Now let us shift to the next presentation by Mr. P.K. Saloni from Engineering Bangalore and Mr. Prashant Dhanpawde, Head West Zone, Triveni Turbines Limited. They are going to make presentation on heat mass balance diagram. The brief biodata of Mr. P.K. Saloni. He is a Senior Manager Engineering at Triveni Turbines Limited. Mr. P.K. Saloni has rich experience in thermal calculations, thermodynamics, and turbine steam path analysis in Triveni Turbines Limited. He had worked for many decades in Triveni Turbine Limited at Bangalore, works in steam turbine shop floor. He possesses multidiscipline and divergent exposure of various aspects of steam turbine generator technologies. He has a deep understanding of heat and mass balance diagram of various applications of steam turbine generator in many industries and heads technologies. Heads technology section in product vertical in proposal engineering for 1 to 100 megawatt power generation. Mr. Saloni has in-depth knowledge of heat and mass balance in sugar plant, sugar cogen and distillery and ethanol TG sets, and worked extensively on Indian and overseas sugar plant configuration. The co-author is Mr. Prashant Dhanpawde. He is Head West Zone Triveni Turbines Limited. He is Head West Zone and has responsibility of Western India and Central India STG business for Triveni Turbines Limited. Ahmedabad, Raipur, Mumbai and Pune offices handles this region and are reporting to him. He is associated with Triveni Turbines Limited for many decades and has rich contributions in sugar cogen in Maharashtra. He possesses strong technical knowledge in thermal engineering, heat mass balance diagrams, mechanical, electrical and instrumentation part of TG Island. More than 100 sugar cogen TG sets of 85 to 520 kg per centimeter square pressure, 105 to 135 kg per centimeter square and 125 to 545 kg per centimeter square steam cycle are supplied under his leadership in Maharashtra, Gujarat, North Karnataka and Chhattisgarh region. Triveni has almost 70% installations based in distillery and ethanol segment. He has worked extensively from Triveni turbine in CPPs, IPP, process cogen, sugar cogen and ethanol and distillery plants for back pressure and condensing TG sets. He is in charge of Triveni Turbine Limited West Zone for proposals, sales, acquisitions, marketing, site installation and commissioning. I request the authors for presentation.
Before we start the presentation, there is an announcement. DST is very happy to announce on 1st of June, we will give another seminar on subject of various alternatives of producing sulfurless sugar, refined sugar, raw sugar and pharma sugar. From 20th of May, the registration will start as we done today. So I request everybody, every industry or every sugar factory people should start doing registration to avoid last moment rush as happened today. Thank you so much.
No registration fee, Sanga.
No registration. No registration fee. This has been otherwise free.
This is necessary for pre-intimation.
I think as I have told everybody, you so we have 25 minutes.
Yeah.
If you can finish your presentation early, we have more time for discussions and interactions.
This presentation will be of much interest to everyone because this is they are very close to their heart. Heat and mass balance diagram of the cogen power plant is very much close to their heart for every technology person.
Sugar factory, everything is to our heart.
Yeah. Good afternoon, dignitaries and my friends and colleagues from Technology Fraternity of Sugar Industries. DST has given us a good opportunity and Triveni Turbine team is pleased to give this presentation on steam turbine heat and mass diagram. This will mainly cover to the basic sugar plant, sugar cogeneration, then distillery and ethanol plants. Triveni Engineering Industries Limited and Triveni Turbine Limited is known to the sugar industry for almost 40 to 50 years. They have the immense contribution to the growth and development of this industry. Triveni Turbine Limited has gone through a technology transformations and infrastructure transformation in big way in last 14 to 15 years. So our few videos will show demonstrate the technology transformations in Triveni. Yeah. Now coming to this, now go previous one. If you see this slide, you will see that it is a very simple, get it connect to the biomass or bagasse and coal and get electricity. That doesn't happen. We have to put the complete plant, is a cogeneration plant, almost of investment of 100 crore to get the electricity and steam for our sugar industry. So how that is achieved? It is done by the Rankine cycle. Next. Now presentation part of it is covered by myself and our technology head, Mr. P.K. Saloni. So basic concept of Rankine cycle and types of Rankine cycle, that will be covered by me, and technology related to the heat and mass balance diagram, how it has been evolved and how it has been constructed or prepared, that will be demonstrated by my colleague P.K. Saloni. Next. Now this Rankine cycle is invented by Mr. William John Rankine. He is a Scottish engineer way back in the last century. He has developed this concept, and that is universally used in any power plant, where the thermal power plant, where the steam is taken as input from any fossil fuel or biomass or coal or any kind of fuel which can burn. From there it is you generate steam, and from steam you generate mechanical power, and from mechanical power you get electricity power. So in any Rankine cycle there are 4 main components. One is a pumping station which increases the pressure temperature of the water, and that is in a boiler. With the combustion it is come to the form of steam, which is high pressure and high temperature. This high pressure and high temperature steam comes into the turbine where it is expanded. During this thermal expansion, mechanical power or torque is generated. When it is fed to the by gearbox to the alternator, it gives us electricity. So this is the concept, and all this thermal power plant operates on this Rankine cycle developed by Mr. Rankine in last century. Next. Now basically there are 3 cycles. Very conventional is very earlier we used to use that 3 megawatt, or you may be familiar with 550 and 290 turbines. These turbines has very simple basic cycle, which is steam is coming to the turbine and it is giving the final output as it is. When there is a lot of progress and development carried out, we come with a regenerative cycle. In normal or cogen, with 2008 concept developed by the Maharashtra state government and Commission of Sugar, when it is evolved with 85 kg cycle and 105 kg cycle, this regenerative cycle concept has come up. In regenerative cycle, we are taking steam extracting in the form of bleed at various stages for HP heater, LP heater and aerator, and that steam is used to increase the heat rate of the plant. With this we will have the less fuel consumption, less bagasse consumption. So this is used for the high technology, that means 85, 105 Atta cycle and 125 Atta cycle. This regenerative cycle is used. Third Rankine cycle is a reheat cycle. Reheat cycle is mainly used in 70 megawatt or plus power plants, or normally our MSCB or utility power plants like NTPC. There they use steam taken from the boiler at mid section, and that has been fed to the turbine in the mid section of the turbine. So it is reheating the steam. So that gives more enthalpy, and then it is converted into mechanical power, you get some more power. So that is the technology's highest invention is reheat cycle. But then mainly it is useful in utility power plant, say 200 megawatt, 600 megawatt and like that. Above 70 megawatt definitely in industrial cycle. Next. Any cogen plant, the major components in TG island is, or cogen plant is steam generator, that is a boiler, we all are familiar. Then is a steam turbine, it is a prime mover. Condenser is a heat sink when it is a condensing turbine. And regenerative heaters, deaerators, LP heater and HP heater. So with this there are almost 4 extraction we are taking from turbine. One is for a process at 2.5 Atta, and these 3 to improve the heat rate of the power plant, these three bleeds. And definitely the pumps, CP and other things are required, polar feed water pump, to make the cycle complete. Next. Now this is a pictorial model of the steam turbine. If you see here, this is the turbine photograph of almost 30 megawatt. So it has gearbox, turbine and its auxiliaries mounted on it. So it is nothing but a prime mover which converts thermal energy into the kinetic energy, and that kinetic energy or mechanical torque is converted into the electrical energy. So this is a cross section of the turbine. This shows you the rotor. Basically it gives you the idea about the steam path. The open section is showing how the steam is flowing inside the turbine. Now same thing will be demonstrated how the steam turbine works and how the heat mass balance diagram improves our efficiency of the plant, efficiency of the cogen plant will be explained by my colleague P.K. Saloni.
Hi, good afternoon everybody. In continuation to the the overall Rankine cycle, so we have gone through various cycles. Within that, steam turbine is the heart of the power plant, where it is a high speed rotating and manufactured with high precision. At rotating at high RPM, it makes a very a critical component. This efficiency is directly impacted to the overall the effectiveness of the power plant or cogen plant. Sir, can you go to next slide? Okay. So just to deep dive into steam turbine, the basically steam turbine works between heat source and heat sinks, between the heat source and heat sinks. So basically the boiler and the condenser. So where it gets the energy from boiler and it loses basically the steam which expands to the turbine.
Mr. Saloni, I'm here. Could you please come down to our subject?
Yes, sir. Next slide. Directly will come.
Don't waste time because these are the basics, huh?
Okay. Okay. Just I will quickly pass through this. So basically, the steam will expand through the turbine, and it will go. It'll pass through the condenser, where it loses the latent heat of the steam to convert back to the water to pump back to the boiler. So we'll go to next one. Okay. So coming back to the steam turbine, like we have different types of steam turbines where we go impulse technology, reaction technology. Under impulse and reaction, impulse technology, we have a Curtis staging and reactive staging. So which is basic this thing. So we'll go to next one. Okay. So just move on. Okay. We'll coming back to the core topic of the today, heat and mass balance diagram. So what is heat and mass balance diagram? Basically, it is a representation of Rankine cycle components, like from boiler to the turbine to the condenser, including the complete regenerative heaters, to see how the steam parameters looks like, along with the process conditions. Because if you go to sugar industry, if you go to paper industry, if you go to any chemical industry, so there are different parameters will be there. So those parameters will be represented in this single diagram. So through that we can directly come to the conclusion that this is efficient, that this is inefficient, or this is suitable for the given applications. So to add to that, so heat and mass balance diagram basically it falls with two theories. One is law of conservation of energy for the total energy, and the equation of continuity. Equation of continuity because we are handling the closed loop cycle, whether it is process or non-process. Heat and mass balance diagram is the closed loop diagram where the total energy and the total mass is fixed, constant. So okay. So while we as the turbine engineers, while we preparing the heat and mass balance diagram, we follow two codes. One is HEI, Heat Exchanger Institute codes, and its guidelines, because Rankine cycle involves a lot of heat exchangers, including regenerative heaters and the surface condenser. Okay, sir. While coming for the audience, while reviewing the HMBD, there are key terminologies which we use. One is specific steam consumption. This is directly says that specific steam consumption is the kg per kilowatt hour, which is the amount of steam utilized in a turbine to generate 1 kilowatt of power. So that is one of the terminology what majorly used. Coming back to the one more major important parameter, that is a turbine heat rate. This is not a plant heat rate. This is a turbine heat rate where we do the balancing of the over plant, where we measure the how much of total energy is consumed by the Rankine cycle to generate 1 kilowatt of power. So that the unit of measurement will be kilocalories per kilowatt hour. So another major parameter is thermal efficiency of the steam turbine. So this is where most of the people will be interested. So this efficiency will directly define the total efficiency of the turbine and effectiveness of the turbine onto the overall cycle. Okay. Okay. Coming back to the few case studies which was given by the DSTI. So we have simulated few HMBD cases for 85 atto cycle, 105 atto cycle, and back pressure and condensing. So this is how it looks like. So you can see, if you see in this cycle, the turbine and in the cycle consists of 2 HPters, that one derator and the auxiliaries and the condenser. There is no LP heater. So we have simulated this for 70 TPH of sugar steam at 2.5 atto. So, okay, go down. So this is the off design. Go to the table, madam. Okay, one more. Yeah. Okay, this is the comparison table. Like we have simulated various cases for 70 TPH process. If you can see, the first one is condensing TG set. The second last this thing back pressure TG set. Under each category we have worked out for 85 atto and 105, 85 and 105. If you go to 85 atto cycle, season 70 TPH and off season 0 TPH. So you can see the various parameters, and I'll deep dive into directly heat rate. So we have kept the boundary condition for all the cases, boundary condition same, and we simulated. The heat rate is working out 1279.5 for during the season. So in the pre-lunch session, Mr. S.T. Barude has mentioned, so we can move to 68 to 69% during cogen. So that is the exactly evaluated matching to heat rate 1280. So if you convert that into efficiency of the cycle, so that will work it out around 68 to 69%. Okay. So always a cogen, a turbine, the condensing turbine which is working with the maximum process will have a maximum efficiency. Go back. No, here. Okay. Go back to the first HMD. Yeah, this is the 105 cycle. You can see the 70 TPH process we have taken. If you numbers are not visible, I will just try to explain. The flow to the condenser is at minimum. During the season, our turbine manufacturer intention is to send the minimum possible steam to the exhaust side with whatever the available vacuum. So that will give you a maximum efficiency of any sugar plant, or even for the case of paper plant. Go back to the table now. Okay. So if you see if you see the comparison between 85 to 105. Now you compare season to off season. Season to season, it is working at 68%. That off season is working at almost 37%. 2,300 kilocalories per hour per kilowatt hour heat rate. It will give an efficiency of almost 37%. This is with the regenerative heat cycle. If you go with non-regenerative heat cycle without HP heater, without LP heater, considering the basic derator, so that maybe is close to 29 to 30% cycle heat rate. So now one more observation what I want to bring to the discussion is that from 85 to 105, if you see the values, the 1279 will drop down to 1250. Okay, so this will be almost close to 6% improvement by increasing the boiler parameter from 85,510 to 105,535. Okay. So now coming back to the comparison between condensing to the back pressure TG state, as rightly mentioned by S.D. Barude sir for the pre-session, so the heat rate is coming down to 895 kilocalories per kilowatt hour. It means that we are speaking in the range of 95 to 96% efficiency of the cycle. I'm not with respect to cycle. So the 4% loss may be all the component loss or main equipment losses. Okay. Go back to the one slide back, man. These are the typical, one of the 5000 TCD plant 70 TPH process we have worked out with the two regenerative heaters, HP heaters, with a 2.5 as a process parameters. Sorry? Oh, I'm sorry. Yeah. Okay, you can see this is the back pressure, but only thing is that disadvantage is that this back pressure cannot be operated during off season case. It is only seasonal. This turbine we can operate only seasonal. Here if you see the power generation, you can see 20.85, 28.4, 22.3, 29.8, and 16.25, 17.5 for the given 780 page process. So this back pressure turbine can be rated to 17.5. We cannot go more than this because you don't have any cushion with respect to condenser. But coming back to this 85 cycle and 105 condensing, so we can pull it to during off season. We can pull it to 29 to 30 megawatt for the same 780 page process. Okay. Go back next man. No, further last. Yeah, these are the another distillery plant. BPTJ 65 cycle and 105 cycle we worked out. Typically this.
Time is short.
Yeah. Yes, sir. We are done, sir. Yeah. What? Okay. Yeah. Thank you. Any questions will be open.
Yes.
Okay.
Hello.
Yes, sir. Sir, just one. This is a distillery plant where we are recently supplying to one of our customers, 7.65 megawatt. So distillery typical parameter exhaust will be 5.5 ATA. And here again, if you talk about heat rate, it will be close to almost 900 kilocalories per kilowatt hour. 65.5 at 480. Because here there is no the one advantage of seasonal operation is that so we can recover 100% latent heat of the water in a cycle. So when we run the water through the complete cycle, it is from minimum temperature to condenser temperature 45 degrees Celsius to we are reaching to 530. While going back, it will go for phase change in the surface condenser. When it go for a phase change in the surface condenser, we are losing 100% latent heat to the cooling tower. So during off-season scenario, when you go for seasonal operations, so we are extracting just before we are extracting the maximum amount of steam, almost close to 80 to 90, up to 80 to 90% of steam in the controlled extraction. The flow to the cooling condenser, it is 10 to 15%. So that way, 70% of the latent heat of the steam water we are not sending to cooling tower. We are using it for the process. So that way, with respect to the seasonal operation and the back pressure operations, it is always on the higher side efficiency, 70% to 90%. Yeah, thank you.
Hello. I want to ask one question regarding alignment of the turbine.
Okay.
When you do the alignment, the main turbine with gearbox, how much down you keep the turbine with the gearbox? Because turbine having heat, that becomes hot, so it lifts. So how much it lifts?
Sir,
Because if you give a chart to, because every turbine the pressure is different, so that accordingly that has to be kept. Otherwise you don't keep it.
विश्वास साहब ऐसा है, आप अकेले उनसे बैठिए, पूरा चार्ट ले लीजिए, हम सबको दे देंगे आपको. जरा ये HMP पे चल रहा है, उसी का सब्जेक्ट चलने दो. बाद में बैठ जाइए, जाने वाले नहीं, आज रुकने वाले आपके लिए रुक जाएंगे.
नहीं कोई बात नहीं, कुछ लेबर खत्म हो गया.
ओके चलो.
And then all the bearings, that is all a lemon bearing or lemon or not lemon.
so we are giving tilting pad bearings actually. Tilting pad bearings we are giving both journal and thrust bearing. Both journal and thrust bearings are tilting pad bearings only. These are most towards the manufacturing details what you are asking, sir. We'll take out the details, but we don't want to discuss in the public actually. We'll give details, sir. We'll give a catalog for the individual megawatt because sir.
You sit with him.
Yeah, sir.
Full chart.
Yeah.
And give it to us, also we'll forward it to everybody.
Yeah.
We will not ask any questions. Okay?
Yes. No. Thank you. Yeah, there's a point from somebody.
Anybody wants to ask any question?
Sir, somebody had a question.
Okay, I would like to raise one pertinent issue. The speakers mentioned Rankine cycle. There are four thermodynamic cycles to study the power generation, in which one is Rankine cycle. Rankine cycle deals with the low pressure steam based power generation, whereas we are going for 110 kg pressure boilers. Steam turbine, okay, which runs on the entropy cycle among the four thermodynamic cycles. Since Rankine cycle deals with the low pressure steam based water technology, then how can they mention the Rankine cycle? I want to make it clear.
Yeah. Basically, Rankine cycle is invented by Mr. William John Rankine, a Scottish engineer. That time the concept was for the low pressure steam cycle. But when it is evolved, the concept remains the same for entire cogen cycle. That means from boiler to the turbine, turbine to the condenser and to the pump. The concept remains the same. How to utilize it and how to convert the heat energy into the mechanical energy, that is a challenge for the developers, designers and engineers. That is how it is evolved. So now this all the cogen, sugar cogen, that is predominantly on the Rankine cycle. Maybe this is a steam cycle, maybe 65 kg cycle, 85 kg cycle, 105 or 125. That is a discretion of the buyer, the consultant or equipment supplier. But concept remains the same. The different cycles are used in a different configuration in the different plants.
Thank you.
Thank you. Thank you, sir.
Yeah.
Meanwhile, second issue. See, we are being Indians, we are proud that we have that Triveni turbines. Okay, as against the tough competition from Japan, Kirloskar Ebara and Shin Nippon. Shin Nippon has given a single TG set at 44 megawatt Varna sugars, whereas Triveni has gone up to 100 megawatt. They have supplied to Bangladesh 90 megawatt. We are proud of our own Indian Triveni being Atmanirbhar, self-reliance policy of the government of India.
तुम्हाला विचारू किती जण येणार आहे?